Okay. And then, we should actually go here. C is 16 multiplied by phase factor, which is 1.
No, the phase.
Oh, I see.
No.
Okay, let me make it a little bit more interesting to come from with my notes. Let's assume that you want to estimate defect density, objective. Find D at the beginning of subsystem test phase. Okay, just to make it more interesting. So, phase factor, if it is beginning of the subsystem test phase, and looking at the table, you expect their higher defect density.
2.5.
Multiplied by 2.5. So, because we have taken system testing phase as the default, so you multiply by 2.5. Okay, and then programming team factor is 1, and maturity level is that is default, and M is that was FM. Okay, how about FS, structure? 20% of the code in assembly language, and so basically it would be 1 plus 0.4 multiplied by 0.2. So 20% of the code is in assembly language. So assembly language code has higher defect density. So you increase 1 by this number. And let us assume that the requirement volatility is usual. And the lower estimate would be 12 multiplied by 2.5 multiplied by this. And so this comes out to be 43.2 per 1,000 lines of code, or sometimes you will say per 1,000 source lines of code. Sometimes you will say KSLOC, and this number is going to come out to be 32.4 per 1,000 lines of code. So your defect density at the beginning of the subsystem test phase, you can expect to be somewhere between here and here. Any questions on this about this example? Now remember that these methods are approximate, and basically you need to calibrate. So C gives you an opportunity to calibrate. So you determine C based on the process at your organization, and by calibrating it, you take other factors into account, and then you assume that everything else is typical. Now it would work best if you use the data for projects which are very similar. For projects which are very different, any model would not be very accurate. So you have to, for some variations, so you are adjusting a couple of factors a little bit, that will give you an estimate of how the defect density will vary. Questions?
No, for the FRV factor, like when we took it last time, there was no set of values compared to that.
Yeah, I think I did give an expression, and so you have to go to our paper, and so basically you have given expressions, and we did not have enough data to come up with the model parameters. And so yeah, go to our paper, history 99, and there's a citation included here. And but there is something that actually we wanted to continue that research, and unfortunately the student graduated. So that was the project, that was the progress made at that time. But I think that is something that we should, we or somebody else should actually look at that more, and there may be some data on that now. I think the Microsoft people, they have some data on CodeChat and some other people. So maybe there is some way. So, but yeah, I think I didn't give you an expression for that, but that's worth revisiting at this point. So all the models need calibration. All the models, they are models, they're not reality. And calibration would be accurate if the data is from similar projects. And some of the factors, one limitation of our model is that some of the factors may be statistically correlated, which probably is not a good idea, because ideally all the factors should be statistically independent. So for example, the capability of the programming team and the capability maturity model, they are actually correlated. So that is a flaw in this model. So it would have been nice if we could combine the two and come up with a single thing that incorporates capabilities of the programming team and the capability and maturity factor. But maybe somebody would do that in future, or maybe we might do that if we get around to doing that. And such models would be very useful at the beginning of project for planning a test effort. So you're a software manager, so you want to decide how much testing resource you are going to need, how many people you are going to need for how long before you will achieve the target defect density. Then these models would be very helpful. However, once your testing has begun, you have started collecting some data from the very same project, then you have some more specific data to rely on, and you will switch over then to the dynamic models. So let us then go on to the next topic, which is software reliability growth. Any questions or comments? Now here, we want to look at software reliability growth, and let me also mention about some of the assumptions. So, now this is the central part of what is called software reliability engineering. And this is related to the famous when to stop testing problem. Now if you are an idealistic person, how many of you are idealistic individuals? Okay, I guess the opposite is more pragmatic or realistic. Okay, so you guys are maybe more realistic. So idealistically, you would say, okay, you have to find all the bugs before you can ship your software. Unfortunately, you will never get there. So when are you going to stop testing? How do you know if your product is ready to be shipped? So basically, given a history of the bug finding rate, when the bug finding rate will drop below an acceptable limit, so the software can be released. Now there's one thing you have to keep in mind, that the bug finding rate during testing is different from the bug finding rate during normal use. And I will mention about this. Okay, let me mention about software test approaches. And you know about a quick background on software testing. So you know that you can do black box testing or white box. and then you can do combination. In black box testing, basically you do functional testing. You're not concerned with
Structure.
how, what is the internal structure, whereas white box is the structural. So your black box is essentially random. Well, I should maybe rephrase that.
Doesn't have to be.
Your black box testing is sort of random.
Yeah.
Remember, random testing, actually, it takes some effort to make your testing really random. So if something could be, if you are not careful, your testing is not going to be random, but it's going to be what can be termed as, let's see, unsystematic.
Mm-hmm.
Random is actually systematic. So, white box testing is structural. You have to keep the structure in mind, and then combination. Now, actually, these applied for both software and hardware testing. And one common approach is to do some black box testing. And in the beginning, testing is efficient, as you know, even random testing. So if you would do random testing, your coverage is going to grow sharply at the beginning, but then less sharply after that. So you could do some black box testing up to here, and then you could generate test cases for whatever is not covered at that time. You can do that with both hardware and software. So you could first do this, and then you could do this. So you can do some combination thing. And test generation approaches. One common approach is partitioning the input domain. This is common. And so basically you have a big input domain. Your test could come from somewhere. And you want to kind of make sure that you test all different aspects of the software. So you will divide your input domain into partitions and somehow draw tests from different partitions. And here, your black box testing, as I was saying, it could be random. It could be anti-random. That I have not talked about, but perhaps I will talk about it sometime. And deterministic. Pseudo-random is actually deterministic. Let's do pseudo-random here. Pseudo-random. Strictly speaking, pseudo-random is deterministic because it's repeatable. The usual assumption when you apply a software reliability growth model is that your testing approach does not change. That's the usual model, usual assumption, and the assumption is actually not often true, and you will see some variation, and I will point out what it will cause. But let's start about the input mix or the test profile. So you have a software that does different things. You could take an input from here, you could take an input that does from here, or you can take an input from here. So how are you going to mix these inputs? So let's talk about the input mix, or the test profile. So profile, depending on how you draw your inputs, can impact the effectiveness of testing. And now what should be the ideal input mix?